Welcome back, everyone, to Merge Conflicts, your weekly developer. No, I'm just kidding, Frank. Welcome back, everyone, to Merge Conflicts. We got an exciting, super duper podcast. I'm James Montemano. That's Frank Krueger. This is Merge Conflict, your weekly developer podcast, talking about all things developer technology and all sorts of good stuff. I do want to give a shout out to our special Patreon members who just got an inside scoop at a whole bunch of electrical work that we've been doing on our house. And if you're interested in that type of electrical work in your life, check us out at patreon.com/mergeconflict.fm, where you get bonus episodes behind the scenes and, of course, podcasts early as fast as I can possibly upload them on the internet. Frank, from my understanding, you have a bunch of these things that we like to call patents. Because you worked at Microsoft. You have like 18 patents. We've talked about it before.
I don't have that many patents. And in fact, I was trying to update my resume. I was trying to track down what patents. I don't have that many. I think I might have, depending on how you count, 3 to 4 to 5.
Well, that is 3 to 4 to 5 more than I have, Frank Krueger. And from my understanding, you're not only a patenter, and if you are a patenter, that must mean you're an inventor.
Oh,
Frank, I believe that you've invented things on the internet. Once again for us, Frank, what are you what's Frank creating and inventing today? And what's he gonna get a patent on?
no patent. I can't afford a patent lawyer. And boy, it's probably not even patentable. So who cares? Don't worry, everyone. No patents here. I should probably put a license because I put a GitHub up. I should probably put a license on it. Hi, James. You started this podcast in a funny way. That's because I told you, James, could we talk about color today? Could we talk about color?
And I think you're GB, baby.
Your mood was so negative, and I'm like, I'll make it good, I promise. Color's fun. Color's interesting. Like, as developers, especially as GUI developers, we deal with color all the time. And pretty much all of us refuse to learn anything about it because, meh.
Yeah.
If you want it red, you put a couple Fs at the beginning. If you want it blue, you put the Fs at the end. Good enough. That's color.
Well, and also, by the way, the platforms and the frameworks for you have simplified it so much. There's like colors dot, and there's system colors, and there's darks and lights, and they just figure out for us automatically. So really, at the end of the day, not only have they simplified that, they've even made the conversions easier, where they, before you'd have to memorize hex and 0 to 255 values. Now you can just convert strings and convert the color red to hex or whatever. Magic.
Now, literally every graphics library on GitHub has a list of 200 named colors because the web went and named a bunch of colors. There's the Pantone named colors. There's all that stuff baked in. But James, what if I told you colors are way more complicated than we think of them as being? Because, like, I guess they are simple, right? You go look up a color name, you go look up some color values, and you pop them in. But what are those color values? What are the fundamentals? I want to talk about what I invented, but I feel like I have to give a little bit of a background. Do you mind if we just talk color theory for like a few minutes? How entertaining is color theory?
This is only a theory, a color theory. Dun, dun. All right, give me your color theory, but I do want to actually give you my theory on color.
Okay.
But it's kind of a conspiracy color theory.
Ooh, so I like it. We'll
get back to it.
I like conspiracy theories. I've heard the color brown doesn't actually exist.
What if I told you, Frank, that all colors don't actually exist, and colors are just a figment of our imagination? That really, that green is not a green. It's only because we've all agreed that green is a green.
Oh, man.
And your green is not the same green as my green. In fact, your green could be red.
Who's to ever know, man? Thank goodness we're not in college and we don't have to spend a whole evening discussing that topic. You had me at the beginning and you lost me at the end. Why does everyone go in that direction? Yeah, perception's weird. Who cares? You can say the same thing about audio. You can say the same thing about taste and smell. But the beginning part of what you said is actually crucially important. And that's actually what I want to talk about hugely.
Wow.
Color doesn't exist. It is a figment of our imagination.
We've agreed on the
But
hex values, just like we've agreed on the value of a dollar. What if I told you
yeah.
that money doesn't actually exist, Frank? It's true.
Well, what if I told you color does exist, but we have to be careful with how we choose our terms?
Hmm.
So I'm going to say it this way. All colors that you know of as a programmer, not going to say as a human being. Human beings experience the world differently than programmers do. But when you're like building a GUI or something like that, when you're building a web page, when you're building the best iOS app ever, you are working in this color space called sRGB. It's RGB, but we put a little S in the beginning. And that's because we color theorists hate sRGB. It is the worst color space on the entire planet. But we use it for historical reasons. It's just what we've got. But here's the fun part. Here's the imagination part. That is called a perceptual color. It has everything to do with how the human body, the eye, the retina, blah blah blah, cones and rods, who cares? All that physiology, biology stuff. RGB and its terrible, ugly step sibling sRGB are perceptual colors. They are not physical. They are not describing a physical reality of light. So color is a product of light, but it's a whole different thing. The colors that we are accustomed to, that especially as developers, are perceptual colors. They take into account how humans perceive light.
Yeah.
So, yeah, it's all in our imagination, but it's also based in reality because there is this real thing called light. But the colors themselves are just a perception thing.
It's kind of like time. We've all agreed the time like there's time, like things are moving, suns go up and down, and we have agreed that days are split into 24 hours, and those 24 hours are split into minutes, and those things are split into seconds, XYZ. And we've agreed that when our watch ticks up a second, we all agree that that is totally good to go, because not only have we perceived that time has changed, but there's a value associated with it. And I think that what's really fascinating about the world around us is that it's actually a lot of perception and math. Like really at the end of the day, like a lot of things are just math. It's just like math coming at us all the time. And I don't think you realize when you're in school. I was talking to my father-in-law because he was a math teacher. You know, there's a math major too. So when I'm talking math, I just am like a dum-dum. But when they're talking math, they're like really smart people. So like, I think it's fascinating because so much math is around us all the time. Like not only are our brains actually calculating math nonstop, like even me moving this microphone like to and from my mouth, my brain is doing some math, right? It's like literally doing computational math of distance and like angles and like stuff like that. And just like, it's crazy. If you could see math, like if you imagine you could see
baby.
math, dude, math would be like everywhere. You know what I'm saying? It's
I don't know what you I don't know
wild.
what you do when you go to bed. I just think about math. I see math all the time, man.
We were doing
it's totally normal.
We were doing this geocache recently, and it had stuff to do with horizons and Pythagorean theorems, and Heather busts out this piece of paper. And what funny this the whole thing is of interest, not about colors, but about math and why. Here, we'll get back on topic. But she brought out this piece of paper. It had like, you know, square roots and like all this like, and this other stuff. And we're just staring at this math, and like we know math and we know trig and we know all this calc and all this other stuff. And we're like kind of stumped by this horizon and this other stuff. But like, it's been a while since like math looked at me at a piece of paper, and I looked at math and I said, I don't know, bro. And that kind of happened. And I kind of felt like I should have known those things. But I do know that math is happening all around us in real time. Like our brains are so cool calculating mathematical things that we equate to like 6 digits of hex. Anyways, that's math. I love math. Math is my favorite. Was your favorite subject math in school? My favorite subject was math.
I look at math as like a tool. So it's
Mm.
not like my favorite subject, but I find it like incredibly important. If I want to study anything else, I have to be good at math because I don't know, it's kind of that universal scientific language. If I want to be good at physics, I have to be good at math. If I want to do chemistry, stoichiometry is all
Electrical
math,
stuff. There's you got to look at, you got to
electrical
subtract.
math.
Yeah.
Yeah.
Plumbing, I mean, when I was,
Well,
you got torque some things. I don't know. I'm just saying,
you
math.
gave a great segue, honestly. Let's talk some math here, buddy, because if color is perception, then maybe we should take a minute and talk about reality. What's really out there? What's actually happening? So, light rays we generally describe as operating at different frequencies. It's a whole simplification of the system. But if you want to think about it, light shoots out of a source, say the sun, shoots out at a ray at the speed of light. It's like a little photon, it's like a little particle, but it's also a wave. It's also jiggling with a certain frequency. It's weird. It's weird. But eventually that photon makes its way to your eye and lights things up at just that one frequency. But of course, there's lots of photons out there. So your eye is actually receiving lots of different photons at different frequencies and different intensities. That is the reality of color. There's these little energetic particles that are hitting your eye at different frequencies. And through the magic of biology and proteins and things, somehow those little photons are turned into signals that go into your brain. So if we want to convert color, a perceptual quantity, a human based perceptual quantity, into something real, then life is a little bit tricky. We have to figure out a mapping from human perception to reality. And that's actually what scientists did in the 20th century. So to this day, we use basically studies that were done 1939 or the general studies where everything is based on color models developed in 1939. I'm not exactly sure how the experiments went, but imagine some poor grad student sitting in a room and some professor just shining lights at him at all sorts of different frequencies and intensities and be like, "Can you see that? How do you feel? Can you see that? How do you feel?" Not how do you feel. Who cares about how grad students feel? But can you see that? That's the important question. And through all these like studies, they were able to develop a chart that converts basically if a human eyeball receives a photon with this frequency, this is how much the person will notice it. It's like given a power, this is how much humans will perceive that
Mm.
light. And like I said, photons are actually coming in. So you'll never get like a pure red frequency photon because it's red with all of its little friends. It's nearby friends coming along and a bunch of other background stuff coming along too. And they all hit your eye and you register them at different things. And then thank goodness for grad students, we are able to convert all those numbers into color.
Color.
So that's how it works. We actually know how to convert from um, physical reality, light, to color. Pretty neat, I
Yeah.
think,
Yeah.
because like it gets back to your original thing of like, what is color? Do we all perceive color differently? Yes, we all do for sure, because there's no absolute system. But at the same time, these grad students seem to agree on what
Yeah.
some colors are.
Yeah. It's really fascinating too because, I'm sure we've all been in a situation where you're looking at, I'm not going to say we've all been, but at least I have. And whether you're, because what ends up happening is you're like, I want to paint this thing. I'm going to paint this thing
Hmm.
white, or I'm going to paint this
Hmm.
thing blue. And then you start to go to Home Depot and you put out the swaths of different colors. And then all of a
It's
sudden
the
you have
worst.
18 pieces of paper that are all white, shades of white.
Yeah.
And then your mind starts to get super confused. You're like, well, is this white? Or is this more
Oh
white? Is
yeah.
this bright white? Is this other white? Like, how much white is white? And is this white?
Right.
And then, like, if you have another person there, they're not perceiving that color 100% exactly. So their white might be a little, it's like you're just going back and
Mm-hmm.
forth with these whites and you're like, oh my gosh, let's just pick a white. So it's fascinating though, to your point of the case in the study, that there's that. And then my dad used to always joke, because he's also colorblind. So he'd always be like, oh, that's that. Like, oh, what color is that? He's like, oh, that's gray. You know what I mean? But it doesn't really,
Yeah.
thanks, Dad. His green and his red were very different than my color, red and green. His were always slights of that. However, what's fascinating about that is it doesn't actually. Now, again, I'm not colorblind. But from what my dad told me, at least in his perception of the color, is, yeah, he knew when something was red or blue or green or whatever color, because it is the shades and instinctually how he can perceive that color, the tones that come through and go there, because he's been taught when he looked at the stoplight, this is red, he can associate that specific tone of red or of
Yes.
gray to red, which gets me back to the original point, which is that color is a lie and it's all that what we perceive to some extent, Frank, even though you just said all
Yeah.
these grad students were like, yeah. However, there might have been
Well,
colorblind grad students in that, right? I assume. No, I
no,
don't know.
no. In fact, this is the neat part of the study, is where they can filter out for probably probably the most important thing in color theory is what you just got to. Everything I just said, all the math, all the physics, all the light, throw all of that out, because humans actually perceive color relatively.
Mm,
We perceive a color relative to colors nearby it. That's actually how our brain in the end interprets it.
mm,
But to remove that effect, they would show just a single color to these grad students.
yeah.
So you're forcing them into an absolute system, even though we all know the stupid dress picture that went around for a long time where everyone saw the dress differently. Perception of color is relative. But if you remove the environment and just put a single color in
Yeah.
front of someone, then you can do some studies. So the caveat is simply, in a space that's all darkness and then just a single color, which is multiple frequencies, is shown through, then the study is done. But you're right. Color is actually relative. If you put tan next to a dark color and tan next to a light color, it's gonna look different to you. It's just the brain and eyes are weird. It's just how they
And
are.
it's what you've been taught at the same time. Like,
Oh yeah,
you,
I'm sorry.
by the way, we are products of our environment, to what you said, which means if someone played a very cruel joke on you and taught you that what we all agreed upon is green is blue, then you would
Oh
assume
yeah.
that the plants behind Frank are all blue right now, because you would say that those are blue because that's the only thing that you know. It is again,
Yeah.
it's like time. Again, if we go back, I'm not a conspiracy theorist, but
Not.
uh not not
Not.
not but if we all actually perceived time differently, we all agreed upon it, then so we get from, we've all agreed that that blue is blue and red is red and green is green. But maybe green is orange. And maybe orange isn't even a color. And maybe oranges are mangoes. And maybe
Is definitely
mangoes
not a
don't even
color.
exist. Dun dun
And
dun.
definitely hummingbirds exist at a whole different time frequency, man.
Whoa,
They are in their own reality.
how do they even flap their wings that fast? Are they even real, or are
Twitch
they
muscle.
robots? They could just be robots. I've always said,
Well,
Frank,
okay.
that when you drive and all of a sudden there's a whole field of cows, those cows aren't cows, they're robots. They're
Uh-huh.
all robots,
The
Frank.
whole world is gaslighting you because we have nothing better to do but to gaslight you, James. The whole
I'm
world's
saying.
against you.
That's what I've
Yeah,
always
it's a
said.
very egocentric point of view.
Yeah, those little baby cows, not baby cows, robots, robots. Just saying. Think about it. Think about it. Think about it.
I'm thinking robot cows, robot. Okay, I'm not going to think about it anymore.
Robot
That was
cows. Just think about it.
You had
We're
a good
all
point, and I
soylent.
was gonna
All soylent.
respond to
The
your good
people.
point, but you've gotten me so distracted with the robot cows. I think I'm just gonna plow forward with what I want to talk about.
Soylent is people. Just saying. Think about it. Soylent Green has forever changed my life. Just saying.
Time is totally relative. Okay, so there
This is
are
this
though.
podcast has gone off the rails 100%,
It
which I
has.
love.
It
But
has.
this
I'm
topic
gonna stop you.
is off the rails, so I
I'm
love it. So
gonna
get
get
us
us
back.
back. Okay. Okay. So we've talked about color is perceptive. We've talked
Yep.
about color is actually based on light.
Yep.
Cool. So that's the
Facts.
physical reality. Now let's talk about real quick color spaces. These are the things we actually deal with as programmers. So let's talk about RGB, for example, real quick. Why do we have RGB? We have RGB because some engineer was able to get something to glow red when he hit it with an electron beam. He was also able to get something to glow greenish when he hit it. Sorry, they hit it with an electron beam, bluish when they hit it with an electron beam. That's why we have RGB, because the first color CRTs happen to glow in those colors, and so we developed a whole color space around RGB.
Was it the 3, or that they could do the red and the blue, and when they combine those two, it was a green,
I'm
or is it actually 3?
simplifying. Yeah,
Oh,
okay.
okay.
I'm sorry. Okay. So there are every possible way you can create color. Because I said, what is color? It's a combination of frequencies.
Yeah.
So any way you want to energize something to make it emit photons at certain frequencies, you can modulate the different frequencies so that what's called a spectrum arrives in the human eye. So at different frequencies, you are getting different intensities at different frequencies. That's called a spectrum. And so let's just simplify for the sake of discussion. Let's say our CRT is an RGB CRT, where it actually has little RGB little lines. You can take a little lens, zoom in, you'll find some RGB somethings. Who knows what pattern they're going to be. So we have a color space RGB, and that's where it comes from. Full intensity red makes reddish. Full intensity green makes greenish. Full intensity blue makes bluish. But if you think about what we've talked about before, we have light, which is reality. We have color, which is human perception. And now we have this whole other thing, which is electrons hitting a CRT. That is a whole different world. So what we need to do is be able to relate these worlds together. So for RGB, we would like to know what the human perception is of it. And you don't need to do this if all you're trying to do is put some red text on a black background. Human gonna perceive that as red text on a black background. No problem. Doesn't matter what color red, because color is relative. It can be anywhere reddish and it'll be perceived as red on a black background.
Yeah.
But if you're trying to do something like create a photorealistic game, now all of a sudden the perception of color that you're emitting on the monitor matters very much. You want the user to experience that color in a very specific way. Where I think this really first came up was printers. You know this world. This is your world.
Thanks.
So, okay. So now we have light, which is reality, human perception of color, which is BS, imaginary. We have these weird things called monitors, which are electron beams hitting phosphorus. God knows what that actually is. And now we have another medium, color printers, which are just bloopy stuff onto paper to try to make color. And so this is why we need to, at some point, usually get back to reality, because we are trying to convert between all these different systems, all these what are called color spaces. And they're all radically different. And they're radically different because honestly, they were designed, they came from the hardware that produced them, the sensors, the actuators that we were able to design, to build. And so that's where I think color space and color theory is actually kind of fun, because if you think about it, it's a maddening problem. It's a very circular problem. Like, how do I get whatever color is on my screen, which is whatever, electrons through phosphorus, coming from a digital signal from a video card, coming from a computer program, and how do I make that computer program emit the right signals to a printer to make that exact same color? And really, the only way to do that is to go from whatever your arbitrary color space is to a physical one, back from the physical one, back to your arbitrary color space of whatever you need to do. So I just wanted to put that out there because I think color spaces truly are maddening, especially when you're in an app like Photoshop and like two blues that should be the same blue. They have like the same RGB hex code, but they render as two different blues. It can really be maddening if you don't understand it. Even if you do understand it, it can still honestly be a little bit maddening because there's so many players at play. But I think it's also really cool too that we're trying to solve this kind of fundamental problem of A, what is color, comma, man? B, can I make this color match that color?
And in how and where you are outputting that color, and we've done this before, right? If you take a photo on your iPhone
Mm-hmm.
and well, one, not only how light and color are captured, if you took an Android phone and an iOS phone
Oh yeah.
and you took photos, like those colors are drastically different. However, if you take the same photo that is on your iPhone and you just send it, like I text it to you, you open it on your Android phone or on your Mac or on your laptop or on a monitor, those color spaces, those spectrums, the contrast,
Mm-hmm.
the things are all very different. Now, if you print them, it's also going to be very different too. In the color
Yeah.
space, we don't deal with RGB. We deal with CMYK, which is cyan, magenta, yellow, and black. Usually CMY. Black is inherent in coloring, but it's there. That's
Assumed.
what I mean. Assumed color, but CMYK, which is the color space in which it's a subtractive color model.
Yeah,
Actually,
it's a weird one.
that's a weird one. But a lot of printers, most printers itself, and ink deals with this as well, which means that those color spaces and the colors that you're printing are gonna not necessarily there. And not to mention, the crazy thing about printers is it's not just like the the ink, but it's the paper, it's the heads,
Yeah.
it's the flow. There's so many
Yeah.
elements to it that are, when you say something is a specific hex color, it is only as good as the medium
Mm-hmm.
in which you are viewing it on. Um,
And
and it's very fascinating to think about.
and what is fascinating is it can actually be exact. Like the color I see on my monitor can be perfectly reproduced by my printer. You brought up the hardest one for printers is the actual color of the paper. Like the printer, they know the color of the toner. That's easy, but the paper is the random variable there.
Yes.
But if you ignore the color of the paper, we can actually, with the correct math, convert between the different color spaces to do the right thing. So at 26 minutes, I think we've covered enough background information, except for one more thing. And then we can actually talk about what I invented and we can get out of here. But first, before we talk about what I actually invented, I want to make fun of sRGB, our FFs and 00s, real quick, okay? The big problem with sRGB, web colors, whatever you want to call them, normal colors, the colors we all know, is it's not a linear space. You can't actually add the colors together. We do it all the time. We add red and blue and we divide by 2. We're programmers. Works fine. You get purplish. It's fine. Stop listening to Frank and his color theory. But it's wrong. You actually can't do that. It's actually a compressed space. So the brightest color in sRGB is white, 111 or FFFFF, whatever scaling you're using. That is the brightest possible color. But as we all know, there is a dramatic difference between a white sheet of paper and staring into the sun. Maybe you perceive both as white. The sun is generally greenish or yellow or something like that. But there's a difference there. There is a sensational difference, and the way that that light interacts with other lights is important. So the problem with sRGB is it just has no dynamic range. Number one, it caps out at 1, and number two, it's not actually linear. So you're by math, the math actually says you cannot add together two RGB values, sRGB values. Not allowed. We do it all the time. It works out fine. But mathematically, you're not supposed to do that. Do you know what you're supposed to do, James, if you want to add two colors? I'm testing you now.
Subtract them? I don't know.
No.
I don't know. Do it.
No,
Convert it to CMYK.
Oh, close, close. You're on the right track. Thankfully, we can convert between color spaces. So if you want to add two sRGB colors together, you first convert them to a color space, fancifully called RGB. It's a lot like sRGB, but it's better.
Yeah.
A little better. Betterer. If you know anything about this stuff, it's called the gamma corrected space or the ungamma corrected space, whichever direction you feel like going. So basically, we turn our sRGB colors into linear colors, so you're allowed to add them. So then you add them, and then you just convert it back to an sRGB. So if you ever actually want to add two sRGB colors together, that's the correct way to do it. Ungamma correct them, add gamma correct.
And a good thing to remember is that there's multiple types of RGBs. There's color match RGB, Adobe RGB, ProPhoto RGB. There's a whole bunch of RGBs because,
Yeah.
also
I'm talking about the standard ones.
The standards. There's the standard one. I'm just happen to be looking at. I happen to be happening to look at the CMYK. But I think that's the interesting part is there are different standards for what these colors mean, right? So are all RGBs created equal? And the answer is no at the end of the day, because people can create their own colors if they want to. Color spaces. They do whatever they want. It's their colors. They figure it out.
In fact, there is a better color space than RGB that we all should be working in, but for historical reasons, we don't. It's the color space that we were talking about earlier in the episode where I said a bunch of grad students said how bad something was blinking and they made charts. We know how the human actually responds to different frequencies. And these are called the tristimulus values. And they were turned into a color space. And that color space, if you know, it's called the CIE XYZ color space. It's usually just called the XYZ color space. So you have the RGB color space and the XYZ. Remember, sRGB is not RGB. Whatever. So there is, in fact, you were mentioning all the Adobe RGBs. Those are all trash too. If you're doing anything at all vaguely related to the perception of color, then you want to be working in the XYZ color space. RGB is nice. RGB is close. But again, RGB is biased towards old-fashioned CRTs. It's not biased towards humans. XYZ, on the other hand, is a very human-centric color format. We should all use it, but honestly, I've been doing colors for 15 years, and I don't usually bother using XYZ in any of my apps. Have you ever heard of it?
If I read the Wikipedia article correct, it's from 1931, the CIE XYZ 1931 color space.
Have I been saying 1939 this whole time? 1931, sorry.
1931, yeah, that's what it says.
It's the result of the study that I was talking about before. This is what they were able to observe, how the human body physiologically reacts to light. It's a color space based on that. Versus RGB, which is a color space based on 1980s monitors.
In my days, I've looked at a lot of color spaces. They're really pretty sort of 0 to 1 type of 0 to 9.
People make graphs, plots.
Graphs. They're very pretty. I've looked at many of them throughout my days of printers and colors and all sorts of things, but I don't know if I've actually coded anything in XYZ color space.
Yeah, it's a good one. No. If you're any modern ray tracer would do this. So in the VFX industry, that's not even true. They're using more advanced lighting schemes than this, but in a world where reality matters, not like GUIs, but photorealistic rendering, that kind of stuff, it matters. Okay, we've gotten all that background information out of the way. Can I tell you what I've invented, James?
I'm ready. Bring it on, Frank.
I invented a new color space.
Of course you did. Of course. Why wouldn't you have? Of course.
Of course. So here's the deal. sRGB, trash. Throw that out. Not going to use that. RGB, better. At least you can add colors together. That's kind of nice. It's a good feature. But otherwise, no good. Based on monitors, throw that one out. Trash also. XYZ. Now, this is an interesting one. But I happen to be writing a photorealistic renderer
Ah, cool.
that could calculate frequency shifts in light. There are different things that can cause light to actually change frequency. So, going from red to blue, for example, if you have an object moving away from you very quickly, it will be red shifted. Its color will just turn more red. This is a lot like, it's called Doppler shift. This is a lot like when you hear an ambulance driving down the road, how the frequency of the siren changes depending on whether it's coming towards you or away from you. The same thing happens with light. The frequency shifts. So I found myself in need of a color space that was a little bit more not perceptual color space. I wanted an actual physical color space, which, as we've discussed, is actually a spectrum. Is a list of at this frequency, this is the intensity of light. At this frequency, this is the intensity of light. At all these different frequencies, here are the different intensities of light. And so spectrums, how do you represent them? Because it's, they can have peaks anywhere, all this kind of stuff. So what I developed was a way to represent a spectrum using just 3 values. So it's just like there's RGB, 3 values, just like there's XYZ, 3 values. There's Frank's 3 values. I call them SX, SY, SZ for spectrum X, spectrum Y, spectrum Z. We'll put a link in the show notes. I won't get into the full technicalities of it, but these 3 values actually define a full spectrum. So not just impulses on the spectrum, but all the other intermediate frequencies also. And so it's a physically real color space based on light. It is basically a 1-to-1 mapping of light, my color space. So that's pretty cool.
Yeah.
It's physically based, not perception based. But in the end, I am writing a renderer. So I'm going to have to go from my Frank's fancy space, Frank's fancy color space, into XYZ or RGB or some color space I can actually output to a monitor. And so when designing a color space, what you want to think about is I want to represent the colors humans can perceive. That's kind of important. In my case, I also want to represent some colors humans can't perceive. Cool, it can do that. But then you, as an engineer, you also have to think about, and in the end, I have to display this color. I need to be able to quickly convert it for display. And also, because I'm writing a renderer, it needs to be able to read texture maps, and texture maps are stored in RGB. So it needs to very quickly, they're actually stored in sRGB, but I'll go from sRGB to RGB, and then very quickly I want to be able to convert from RGB into Frank's fancy physical format. So what I'm very proud of, I'm proud that my color space is only 3 values. I'm proud that it is an actual physical color space. It has a direct mapping to light. But I'm also incredibly proud that you can convert between RGB and my color space and my color space back to RGB with just a normal 9 multiplications, a standard way. We call it a linear conversion between color spaces. So my color space is linearly convertible from the perceptual color spaces. So in just a few multiplies, you can quickly go from a perceptual color space like RGB to my magical color space. Do all your physics in my awesome color space because it's reality and it's real and you can do real math there. And then when it's time to slum it and display these colors to the user, you can convert back down to a perceptual color space like RGB and then trash it all the way down to sRGB, maybe a little tone mapping on the way in between. And then you have a physics-based renderer. So there's my invention. Is it worth a patent?
Maybe.
I like it.
It could be. I'd love to see it in action, that's for sure.
It works pretty well. I'll send you a demo eventually, but the demo's not that good looking, so it's not really showing it off. I want to be like, yeah, colors, they're pretty ugly. But yeah, I'm pretty happy with it because it checked all the boxes for me. It's physically based. It's super efficient. I can convert between all the other formats, and also it's linear. Unlike our sRGB, if you want to add two of my colors together, you know what you do? You add them together. It's fine.
I like that. That's cool.
Reminder, you can't do that in an sRGB, but in my space, you can. And also, my space, because it's energy based, it's the actual numbers you're putting in there are energies. It's HDR. It's naturally HDR.
Oh,
So
cool.
you can do HDR rendering, you can do physically correct rendering, and converting to real colors, practical color spaces. It's trivial. That's my invention, James. Thank you so much for letting me talk about it. And thank you so much for letting me talk about colors for 30 minutes so I could actually say what my invention was.
No problem. And just like colors are a lie, so is Spec 3. They're all lies, Frank, all the way down and all the way up. No, I'm just kidding. No, this is pretty cool. I love math, and I think that this is pretty neat. I think that it's while it may be easier to memorize FF00000 compared to 001.190, but probably nothing.
001 would have worked fine.
001, yeah, exactly. But I still think it's pretty cool that you went through the theory and effort and energy to do this, and to have a really great readme that kind of walks through everything that we talked about tonight. So if you're really into color theory, you're really into math, definitely check out this repo. And thanks for walking us through it, Frank. I had fun, and thank you for letting me jest about conspiracy color theory. So, and
Look,
that
man,
was just a theory, a color theory. Bam.
when we want to talk about the non-existence of time, I'm here for that again, but that might be a separate episode.
I would like to believe. Let's do it. All right. Well, that's going to do it for this week's Merge Conflict. Let us know what color space you've created by running into the show on our YouTube page, youtube.com/@Merge Conflict FM. You can also leave reviews, comments, all that stuff, and wherever you watch or listen to this podcast. Share it with a friend, do a thing, like, subscribe, do all the things. Become a Patreon subscriber, patreon.com/Merge You can become all this stuff. It's on the show notes below. That's going to do it for this week's podcast. So until next time, I'm James Montemagno.
And I'm Frank Kruger. Thank you for watching and listening.
Peace.